So, very good evening to all of you. So, this will be the second class of chemical measure trace and ultra trace analysis. And here is my mail ID. If in last class you have missed, then you can write it down here. This is the mail ID, the DRC mail ID and Gmail ID also. I have not received any query from anybody for last class. So I am hoping I may receive something from all of you in my next few lectures. So in today's lecture, last lecture we have covered this one. In today's lecture, we will be covering the sample storage, preparation, separation science, and chromatographic techniques. So the content of this lecture is sample storage and preservation, sample preparation, separation of analytes, and chromatographic techniques. So let us go through one by one. So sample storage and preservation. Why to store a sample? Because it is not that always when we collect the sample, it will be analyzed immediately. There is always a time gap between when the sample is taken and the analysis is being carried out. And therefore, during this period of sample collection and analysis, the sample can or it can be contaminated by foreign matters. Analyte may lost during storage, spillage, precipitation of analyte may happen. Also, the sample may decompose or evaporate, which will change the analyte concentration. Or sometimes, if any volatile impurities are there, they may lose. And therefore, there should be proper storage of sample till you are analyzing it. So now you can imagine different types of sample may be there. It is solid sample, liquid sample, or gaseous sample. So let us see just broadly how this sample can be stored. Like for solid sample, you can use airtight containers made up of inert material, for example, glass or that is polytetrafluoride to avoid contamination. Then hygroscopic solids, that is sometimes like salt, which can absorb moisture, should be kept in a desiccator to prevent absorption of moisture. Use of opaque or amber container for light sensitive solids like silver salts. Then thermally sensitive solids should be kept in temperature controlled environment, like you may refrigerate it or you may use deep freeze conditions. Labeled sample bottles include details like sample name, date, and storage conditions. Because it is not that you are receiving only a single sample at a time. There may be large number of samples. So if you are not labeling it properly, then there can be exchange of samples and then sample may lose its identity. And therefore, you have to include the details like sample name, date, storage condition, etc. on a sample. In case of liquid samples, it can be stored in chemically resistant material like borosilicate glass, HDP, high density polyethylene, that is HDP, or PTFE, depending on the liquid's properties. It is acidic, basic, or volatile. So you need to keep it accordingly. Then seal the containers tightly to minimize evaporation, because you all know whatever may be the liquid, it tends to evaporate. And if it is getting evaporated, then the analyte concentration will change. So you have to minimize the evaporation, especially for volatile liquids like alcohols or solvents. They tend to evaporate very fast. Then refrigerate or freeze temperature sensitive liquids like biological samples, volatile organic compounds. Avoid cross contamination by using separate containers for different liquids and clean tools between handling. Store light sensitive liquids, for example, chloroform, in amber glass bottles. For gaseous samples, special accessories are available for sampling. Precautions to be taken for storage. example, say in the air pollution, you want to analyze SO2 in the air, but it is not stable. If in the air oxygen is there, then it will form SO3. So you will not be able to know the exact concentration of SO2 when you are going to analyze the sample. So to avoid this, you have to store the sample at 4 degrees centigrade. So the sample should not react also with the walls of the container so that its identity should be maintained. So now gas sampling, you can see this type of vessels are available which can sample the gas. So there is a stop cock and you can attach it to a cylinder from where gas will be entered into this, and then you can close the valve. So the gas which you want to analyze should be gas in this type of vessels. Now these are the sample storage. So in my last class also I have given you something on sample preparation. I have told you the various dissolution techniques like acid dissolution, alkali dissolution, microwave dissolution, the high pressure dissolution. So you may go through that for this sample preparation. However, few points I want to add in this lecture also, and that is sample preparation is a crucial step in chemistry to ensure that the sample is in a suitable state for accurate and reliable analysis. What does this mean? Say, for example, you just imagine you have taken some soil sample in which you want to do iron by spectrophotometry. Then you all know that the spectrophotometer only solution sample can be done. So now the soil sample has to be dissolved and bring into solution form. So that is where you need to prepare a sample. So whatever may be the sample, there will be bit of preparation is needed when you want to use some technique where you are going to analyze that. So depending on the technique, you need to prepare your sample. So this is technique based. Some technique may take solid sample directly, but most of the technique accepts solution samples. So you have to prepare the sample. So there are some key steps which involved during the sample preparation. That solids are usually first grind, mix, or blend to a consistent texture and suitable particle size, which ensures homogeneity in the sample. Because while you are taking a small sample size from a big one, then it should be a proper representative of the total big sample size. Therefore, you have to homogenize it, grind it, mix it, and blend it. Then for environmental water samples must be filtered through 0.45 micron filter paper before analysis for its metal content. And care should be taken for incomplete filtration, losses of analyte due to suction on filter paper. So these are few things you have to take care of. Now for solid samples, you have to choose a solvent. It may be acid or alkali. It all depends on what is the sample type, of which I have given one example each for this type of dissolution in my first lecture. So you may go through that. So for solid samples, a solvent is chosen that dissolves the whole sample without decomposing the analyte. For metal, iron and all, it is fine. But if your analyte is some organic, you have to take care very much about this, that organic components should not be decomposed during the sample preparation. Also, care should be taken for incomplete dissolution of the analyte, losses of analyte by volatilization, introduction of analyte as a solvent contamination, contamination from the reaction of the solvent with the vessel wall. This all care should be taken. And whenever you are doing one analysis, you always have to do replicate samples. What is the meaning of replicate samples? You have to analyze 3 times, minimum 3 sample aliquot has to be taken from the main sample and processed in a similar way, and finally they should. So replicate samples are always performed unless the quantity of the analyte, expense, or other factors prohibit. Means if your sample size is very small, Say, for example, forensic sample. You are not having very high quantity of sample. You cannot do replicate sample. Like that, if those cases are there, then okay, you that is the constraint, but otherwise you have to take replicate samples. Replicate samples are portion of a material of approximately the same size that is carried through an analytical procedure at the same time and the same way. Obtaining replicate data on samples involves the quality of the results and provides a measure of the reliability. So obtaining replicate data on samples improves the quality of the results and provides a measure of the reliability. So therefore, replicate samples are very much needed when you are doing an analysis. Now, once you have prepared the sample, you have finalized the instrument. Now, there may be many other things in your sample which may interfere during analysis. So, it normally happens that you need a separation technique before analyzing your analyte. So, that is to interfere, the eliminating interferences. So, separation steps add to analysis for eliminating interferences, as well as if your analyte concentration is very in ultra trace region, so you can pre-concentrate your analyte, so it will be bring into the detection range of the instrument you are going to use. So separating the analyte from sample is a crucial step in analytical chemistry to eliminate interference and thereby ensuring accurate and reliable results. So now these are the various approaches that again depends on sample to sample what approach you should use for separating the analyte from your matrix. So for example, physical separation techniques are there, filtration. So the principle here is removes insoluble particles or precipitates. Then one example for each case I am giving. The example is separating suspended solids before analysis. In application, you may apply it to environmental waters. Just in before slide, I have just told that environmental waters need to be filtered through 0.45 micron filter paper before subjecting to analysis. So this removes all the insoluble impurities and also sometimes the turbidity. Now centrifugation, the uses centrifugal force to separate components. This isolates blood plasma from cellular components, and it is very much useful in case of clinical chemistry for serum analysis. Then decantation separates layers in immiscible liquid systems. An example is decanting organic solvent from aqueous layers in solvent extraction. Then solvent extraction, about this we'll take it bit elaborately, therefore there is different color code is provided. What is the principle here? You all may be knowing that solvent extraction transfer of analytes or interferences between two immiscible liquids based on the solubility of the analyte in these two layers. Examples being extraction of organic analytes into non-polar solvents, removal of polar interferences from organic layer. Application is isolation of pesticide, drug residues, etc. Now precipitation. This is also an important separation technique which converts interferences into insoluble forms by adding specific reagents. For example, adding barium chloride to remove sulfate ions. You know that barium sulfate gets precipitates. and also precipitating protein in biological sample with trichloroacetic acid. The application is in water analysis and sample cleanup in biomolecular studies. And there are also another thing called as co-precipitation. Co-precipitation. That is that when we separate the analyte as precipitate, we add some reagent, excess of some reagent, which we take the analyte with itself to get precipitate, and thereby separating it from the major matrix which remains in the soluble portion. Precipitation is separating the matrix, whereas co-precipitation is separating the analyte. Now, chromatographic techniques are there, in which there is gas chromatography, which separates volatile components based on boiling points and interactions with stationary phase. HPLC, that is high performance liquid chromatography, which separates analytes from interferences based on polarity, size, or ion exchange. And size exclusion chromatography, which separates based on molecular size of the analyte. And there is another term called solid phase extraction, or normally it is SPE. Here, adsorption and subsequent selective elution of analyte or interferences on solid sorbents. So you have to take solid adsorbents or sorbents that may, because it can adsorb or absorb. Therefore, altogether it is just called sorbents. And here your analyte will be sorbed on the solid phase, and then you again separate the solid phase and elute the analyte. Example being sorption of analyte on polyhydroxamic acid beads. Application is environmental remediation. Then ion exchange, the principle is removes ionic interferences by exchanging ion on a charged regime. Example is cation exchange regime to remove metal ions and anion exchange regime to remove chloride or sulfate ion. Application being water treatment, production of deionized water. You all know deionized water is very much required in an analytical chemistry lab, which is being used for analysis purpose for all water works. We use that only, from which all the contaminants or all the metal ions are being removed using ion exchange column. There are various advanced techniques of separation. Those are electrophoresis, which separates analytes based on charge and size under an electric field, and therefore electrophoresis. Then supercritical fluid extraction, which uses supercritical fluid, for example, carbon dioxide, to selectively extract components. Dialysis and ultrafiltration, which uses semi-permeable membranes to separate small molecules from larger ones. So these are the various separation techniques. Now the choice, as I have told you, there are numerous separation techniques are available. You have to choose the best one which will suit your sample. So it depends on the nature of the sample, whether it is a solid, liquid, gas, or type of interferences, whether it is a physical, chemical, or spectral, and requires sensitivity and accuracy. Many other points are there. These three are the major points which I want to convey you. So depending on this, you need to choose one. Careful optimization of separation conditions ensures effective removal of interferences and enhances your analytical results reliability. So now we'll see two of the important separation techniques bit elaborate. That is solvent extraction and ion exchange and beta chromatography. So now let us look into the solvent extraction. What is solvent extraction? It is a very important separation technique. This is the separation technique that transfers a solute from one liquid phase to another based on its solubility. Out of the two liquid phases, one is usually aqueous and the other is an immiscible organic phase. This is also known as liquid-liquid extraction. So never get confused if somewhere you see liquid-liquid extraction. This is nothing but the solvent extraction. So this is the pictorial depiction. You can see there are two phases. This is phase 2, this is phase 1. These two are immiscible, having a proper boundary. So now your solute, say S, is distributing between these two, and this is the equilibrium constant of this distribution. So K is given as S2 by S1. Now the partitioning of solute S between two phases 1 and 2 is described by equilibrium constant K, and where this K in this case is termed as partition coefficient, because it is partitioning between the solute is partitioning between immiscible layers, therefore it is known as partition coefficient. Now, what is the advantage? What are the advantages of solvent extraction where it is used widely? Because it provides selective separation, it is scalable and versatile. You can use it in your lab scale also for small work, and it can be used in plants also. So it is scalable and versatile, and it used in analytical and industrial applications. So now what is the principle? The separation or the distribution of the solute between these two phases is based on Nernst distribution law. It states that at constant temperature, when two immiscible solvents are in contact with each other, then solute distributes itself in the two immiscible solvents, and at equilibrium, the ratio of concentration of solute is fixed. So this is a fixed quantity. This is constant. So total concentration, and then on what this depends? On the solute, and what is your organic phase, and what is your aqueous phase. Once these three are fixed, then this is a fixed quantity. So it defines as the total concentration of solute in organic phase and that in aqueous phase. So now let us see the various terms associated with solvent extraction. And just you have seen, it is the distribution coefficient or distribution ratio also it is called. So total concentration of solute in organic phase by total concentration of solute in aqueous phase. Higher the value of Ke indicates better extraction efficiency into the organic phase, obviously, because organic phase is in the numerator. Then Ke depends on solubility, temperature, and solvent polarity. Now here we assume two things, like all the solvent extraction concept is based on few assumptions, and the assumptions that the two liquids are immiscible to each other, the solute is soluble both in both the phases, and the solute presents same form or state in both phases. No association or dissociation is happening, or no interaction with the solvent is happening. There is another term called separation factor, because when you are using solvent extraction, there may be many elements in your sample. So while extracting or separating the analyte, it may associated with some other element also to which you are not interested. So if the solution contains more than one solute, which normally is the case, because you will never get a case when only one solute or one analyte is present. So when more than one solute is there, let us consider A and B, and condition is such that although solute A gets quantitatively extracted, at the same time B also be extracted, then the effectiveness of separation can be expressed in terms of separation factor. So what is it? This is the equation for separation factor. Then for A organic by B organic divided by A aqueous by B aqueous. And finally it gives the separation factor is nothing but the distribution ratio of A by distribution ratio of B. A distribution ratio or distribution coefficient. And there is something I want to just convey to you, that if separation factor is greater than 1, then effective separation happens. If beta equal to 1, then there is no separation. And if beta is less than 1, then there is a poor separation between these two. There is another term, extraction efficiency or percentage extraction. So percentage extraction is that amount in organic phase means amount getting extracted to the total amount multiplied by 100. So that is the percentage extraction. So the fraction extraction is this amount in organic phase by total amount, which you can rate like the element or analyte total concentration is distributed between organic and aqueous. So whatever is extracted in organic and then aqueous will be total. So now if you want to derive, then finally you will get an equation like this, where R, this R is the phase ratio. And what is the phase ratio? Means the volume of organic phase to volume of aqueous phase. So this is totally dependent on you. What is the ratio you are taking? You may take it as 1 or you may take it different. Like if you are taking 0.5 ml of organic and aqueous is 1 ml, then ratio will be different. If you are taking both 1 ml, then ratio will be 1. So depending on that, the phase ratio is there. And now this is the, if phase ratio is 1, then this is the percentage extraction. Then phase ratio, what I have just told you, volume in aqueous phase by volume to organic phase. So this is there. Or either case, that is your, you can take it, reloading capacity or maximum amount of solute that can be retained by organic phase. This C max equal to saturation concentration of solute in organic phase. A higher loading capacity reduces solvent consumption. Now you have to remember few points when you are using a solvent extraction as a separation technique. In case of inorganic solutes like say metal ion, although have high aqueous solubility, you know metal ions are charged ones. And when it is a charged one, it has higher solubility in water, in aqueous medium, but have extremely low or insoluble in organic solvent. Then how to use solvent extraction for metal ions? So that time the metal ions must have to convert into neutral metal chelates or ion association complexes to make it soluble or extractable in organic phase. And also, like solvent extraction you are doing, say you are extracting iron to some aqueous phase. Or you are like uranium, you know, uranium, if we are doing all the impurities in uranium you want to do, then you have to extract uranium to TBP. So that time you can perform a single extraction or you can perform a multi-stage extraction. So percentage extraction in multi-step extraction is higher than a single-step extraction. So normally multi-step extraction is more beneficial because say in a single extraction it is extracting 80%. Now 20% is still remaining in the aqueous phase. So if you are extracting once more, then 80% of the 20 remaining will be getting extracted. So therefore, if you are doing multiple extraction, then almost total analyte can be extracted to organic phase. So I want to do one small assignment for all of you. Should calculator derive the formula of for amount of solute remain in aqueous phase after single extraction and after nth extraction. So this is a small homework for all of you. Now let us see what is the driving force or how if a metal ion needs to be extracted to organic phase, then how to do that. Because just as I have told you, metal ions are charged ions and they are solvated by water molecules and present in an aqueous solution. And extracting them to organic phase is not possible at all because they are charged one. So in that case, as I have told you, you can complex it or some ion association complex may be formed, or like that you have to do various things so that it could be extracted to organic phase. Now let us see first one, complex formation. So with one example we see each one how it can be extracted to organic phase. So for complex formation, the example I have taken is extraction of zirconium from a solution containing both zirconium and niobium in concentrated HNO3 solution. They are now present in aqueous phase. So for this extraction, you need to take the organic phase, either xylene or toluene. Then you have to use a complexing agent, TTA, thionyl trifluoroacetone. The structure is like this. So now you know zirconium in aqueous solution, it remains as zirconium 4 plus and highly charged. So when this interacts with HTTA, it will form a complex which does not have any charge. Now this can go to your organic phase very easily. So the hydrophilic nature of zirconium 4 plus is drastically reduced after complexation with TTA, and this complex is formed which is being extracted into the organic phase. So this is one example of complex formation. Second one is ion pair formation. So for this, I have taken the example of extraction of iron 3 plus from aqueous solution containing HCl. So the species normally exists in the solution is this one, which is solvated. Now the extraction here is carried out using diethyl ether. So this is the thing which is present in aqueous phase. Now this is the ether. So here the solvent itself is replacing water and this is forming. So this is the ion pair formation. Now this can go to very easy to organic phase and hence you can separate it. Now coordinated neutral species. So extraction of uranium 6 from 4 molar HNO3 medium aqueous phase using TBP or tri-N-butyl phosphate in dodecan. So TBP directly is not used. It is used as 30% or 20%, that depends on your procedure, with dodecan, or in kerosene. Sometimes kerosene also can be taken. So this is the structure. This is the equation where TBP is replacing the solvent water molecule and then it is going to the organic phase. Now let us see some examples where solvent extraction is used extensively in DAE. So what is DAE? DAE is the Department of Atomic Energy, where it is being used. So separation of uranium from its ore, separation of uranium and plutonium from fission products in spent fuel. In both the cases, TBP is used for the separation from nitric acid medium. Then thorium separation from ore, uranium-233 separation from irradiated thoria. In both the cases, again TBP is used for separation from nitric acid medium. Zirconium, as we have seen the example, zirconium is used for the preparation of clad and pressure tube materials in nuclear reactor. Because of similar chemical properties, hafnium also present with zirconium. Now, hafnium is not at all desirable in nuclear reactor because it has a very high neutron absorption cross section, and so it needs to be separated from zirconium. In that case, you have to use MIBK, that is methyl isobutyl ketone, used for separation of hafnium from bulk of zirconium. Gadolinium also used in nuclear reactor for control or excess reactivity, as it possesses very high neutron absorption cross section. Gadolinium needs to be separated from monazite. So here di-2-ethyl hexyl phosphoric acid is used for this purpose. So these are few examples of solvent extraction being used in Department of Atomic Energy, which you all should know. Now next, let us see the ion exchange. So what is ion exchange? The term ion exchange is generally understood to mean the exchange of ions, like ions or similar charge between a solution and a solid medium, in contact with solution and highly insoluble to that medium. So based on the structural material composition, the ion exchanger used for the separation can be divided into two types. First one is inorganic ion exchanger.
Second one is organic ion exchanger. Let us see one by one. So what are the inorganic ion exchanger? There are mainly three types of inorganic ion exchanger: zeolites and clay, hydrox oxides, and ammonium phosphomolybdate. Now, zeolites and clay, these are actually hydrous aluminosilicates as shown in this picture, where SiO4 and AlO4 are the two structural units. At some sites, if SiO4 is replaced by aluminium 3, then the backbone structure of zeolites clay remains negatively charged because you are replacing 4 plus with 3 plus. So, for charge neutrality, alkali or alkaline earth metals ions like Na plus, K plus, magnesium 2 plus or calcium 2 plus were accumulated inside the pores of the 3D structure. These ions are mobile and hopping throughout the network and are liable to exchange with other ions, which imparts the ion exchange behavior. So there are some fundamental difference between zeolites and clay based on their structural viewpoints. Zeolites are 3D network of SiO4 and AlO4 together, whereas clay is a layered structure of SiO4 and AlO4 units respectively. So these are the clay, this is the zeolite. Then hydrous oxide, this is example is silica, titanium oxide, zirconium, iron oxides, etc. They are highly unselective and unspecific. The exchange behavior highly depends on the pH. It depends on the pH of the medium. Generally, the exchange capacity for cation increases with increase of pH of the medium, but the capacity becomes low in acidic medium. So the surface wedge groups introduce ion exchange nature in hydrous oxides. Next one is ammonium phosphomolybdate. And this is the formula. It has a cage-like structure, as you can see here. This is a cage-like structure. And the ammonium ion generally exists in that cavity and it is labile for exchange. So this is used for the separation of cesium-137, which half-life is around 30 years, from the radioactive wastes. So last, which is more widely used are the organic ion exchanger. What is an organic ion exchanger? It is a functionalized polymer of 3D network having highly porous structure through which the mobile phase, that is water, can pass through. And they are highly insoluble in aqueous medium but have limited solubility in organic solvent. Some commercially available ion exchangers, the trade name are DOX50x8 and DOX1x8. DOX50, it suggests that it is a cation exchanger, and DOX1 means it is an anion exchanger. And what does this cross 8 means? We'll just see ahead. So you can see the DOX50 and DOX1. It is a styrene divinyl benzene network. So this is the flow sheet of its base material preparation, where styrene is there, and this is divinyl benzene. This one vinyl, second vinyl, so divinyl benzene is there. So this is the network, how it is formed. So this is the flow sheet for the production of styrene divinyl benzene or DVB based on ion exchange resin. Now this resulting material is seen like this. So the resulting material have good porosity. Water molecules pass through it so that the exchange process of the solute between the mobile phase, that is aqueous medium, and the stationary phase resin can take place smoothly. So now if you see the classification of organic ion exchanger, it goes like this. Ion exchange resin, it can be cation exchange, as you have just seen, DOX50, and then anion exchange, that is DOX1. And again, cation exchange can be strong acidic or weak acidic, and anion again strong basic or weak base ion exchangers. So now let us see what are those. Weak cation or anion exchanger. Weak cation exchanger contains groups like COOH or phenolic group or phosphinic acid group. Weak anion exchanger generally contains group like NH2, NHR or NR2. So these are not good as strong cation or anion exchanger because of weak dissociation constant. As you know, the COOH is a very weak acid, so that dissociation constant is very weak. So these work in a specific pH range only, unlike the strong cation or anion exchanger, which works throughout the pH range. So here it is given, you can see the strong and weak for cation exchanger and the strong and weak for anion exchanger. So these are the group where here the H plus is the exchangeable ion and this is SO3 minus is a part of the resin, and this is loosely just attached there so that it can be exchanged, and its working pH is 0 to 14. In case of weak, it is COH or AROH. It is greater than 7 pH, it works. Similarly, for anion exchange resin, it is Nr3 plus OH minus. So this is the exchangeable ion which can be exchanged with any anion, and this is for weak. This is the primary amine, secondary amine or tertiary amine groups are there. So this is the works in pH less than 7. So now what is divinyl benzene where it is required? And what is that cross site, whatever we have seen means? So actually role of DVB is that it acts as a cross linker. Cross linking imparts rigidity or hardness to the resin. Means there will be forming different polymer chains, and these two chains will be joined if DVB will be there, because it has two polymerizing groups. One is one vinyl group and the second vinyl group. Both are polymerizing. So it will act as a cross-linking between two polymer chains. So it acts as a cross-linker. Cross-linking imparts rigidity, hardness to the resin. It makes resin denser and insoluble in aqueous medium. It helps in achieving porous 3D structure. The DVB concentration is very much crucial for ion exchange resin. If it is cross 4 means 4% of DVB. It is less cross-linking, less rigid, results very high swelling in aqueous medium, which may lead to breakage of the resin bits. Cross 8 means 8% DVB. Best for laboratory use, cross-linking, hardness, mobility of aqueous phase, everything is optimum. Cross 12 means 12% DVB, very high cross-linking, which leads to high hardness, and this again results very slow swelling, mobility of aqueous phase through the pores of the resin becomes very low because of very low swelling. Now the difference between inorganic and organic ion exchange resin, what is the difference between these two? Is that inorganic may be natural or synthetic. Organic is definitely a synthetic ion exchanger. Inorganic is again composed of inorganic oxides or hydroxide, just we have seen. No carbon content is there. Here it is carbon is the main backbone structure. It is thermal and radiation stability is very high. It is low. Selectivity is very high as the pore size within the rigid structure is specific. Less selectivity because it is just exchangeable. So any cation can exchange with the H plus or any anion may exchange. Operating condition, especially the chemical environment, should not be very harsh. It can withstand any chemical environment. Regeneration is possible by NaCl KCl solution, but regeneration using acid base is not possible. Regeneration is quite easy. Exact capacity determination is very difficult. Here you can determine it very easily. Now, what are the various terminologies associated with ion exchange process is that again the distribution ratio. Here it is the amount of metal ion in resin by weight of resin and amount of metal ion in solution by total volume of the solution. So this is the distribution ratio. There is small difference between the distribution ratio in case of solvent extraction and here. You can mark that. So its unit is milligram per gram, milliliter per gram or liter per kg. Separation factor is here. Again, it is there like in solvent extraction, and selectivity coefficient. So say this is resin A plus B, resin B plus A. So the selectivity coefficient is defined like this. And another term is elution. It is the removal process of the ions from ion exchange column. Eluent, it is the mobile phase of the solvent that is passed through the column for removal of ions. Eluate is the solution of adsorbed materials in the eluent obtained during the process of elution. So eluate is eluent plus adsorbed ion on the column. So these elution, eluent, eluate, and all these terms will come very often when you will work with the ion exchange processes. How to calculate the capacity of an ion exchange resin? So ion exchanger resin contains certain amount of exchangeable groups which take part in ion exchange process, and the quantitative representation of the total exchangeable group in the resin is called exchange capacity. And the unit of exchange capacity is nothing but milli-equivalent per gram of resin when resin is dry weight. Because you know that resin, when you put it in aqueous medium, it absorbs water, it swells. But the capacity is defined as per the dry weight. So for example, let us take one case. Capacity of resin is 5 milli-equivalent per gram of resin for Na plus ions. What does this mean? This means 1 gram of resin, dry resin, can hold 5 milli-equivalent of sodium plus ions. So now what does means by 5 milli-equivalent? You know that equivalent weight of sodium is 23 gram. So milli-equivalent is nothing but 23 milligram. So what is 5 milli-equivalent is 5 into 23, that is 115 milligram of sodium. So 5 milli-equivalent per gram of resin for sodium plus ions means 1 gram of that specific resin can hold 115 milligram of sodium plus. So this is what the capacity means. Now, what are the various factors governing selectivity? Because as you know, ion exchange can exchange ions. Cation exchanger can exchange cations, anion exchanger can exchange anions. So in a solution, you may have many cations, many anions. Then how does that selectivity will be affected? So as you know, one factor is charge on the metal ion. So as ion exchange is an electrostatic phenomenon, the selectivity directly depends on the charge on the ions. Selectivity is proportional to the charge on the ions. So the elution order is exactly reverse to selectivity order. So once selectivity order means it is going and sitting on the ion exchanger. And elution is you want to remove those ions for your use in analytical purpose from the resin. So that is elution. So once selectivity, the order of selectivity and elution is just reverse. So you can see the selectivity is, if it is highly charged, so zirconium 4 plus will strongly bound, then lanthanum, then calcium, then potassium. So elution, first potassium will come out, then calcium, then lanthanum, and then zirconium. Similarly, in case of anions, phosphate and sulfate. So phosphate is more charged than sulfate, so selectivity order will be this. The expected elution order is phosphate should be less than sulfate. But this many times it depends on the condition. So every time it is not that your elution order will be exactly reversed to selectivity order. Because in case of dilute NaOH is used as eluent, then it is observed that phosphate comes out first, whereas it should be expected later, first should sulfate. But then you observe that phosphate is coming out first when you are using dilute NaOH. This is because in case of at pH 9, phosphate actually exists as HPO4 2 minus. Now you see, now this ion charge is same with sulfate, and therefore the order changes. Another one is hydrated ionic radii. Selectivity is inversely proportional to the size of hydrated ionic radii. Smaller is the ion, higher will be the ionic potential. That is higher charge density over the ions, and this leads to enhanced hydration. So now you can see lithium plus, sodium plus. So hydrated ionic radii of lithium plus is higher than sodium plus. So selectivity order will be sodium plus is greater than lithium plus. And elution order will be again the opposite. Lithium will be first coming out, then sodium. Similarly, you can see the case of fluorine, chloride, bromide, and iodide. So these are the orders. Now how this procedure, like if you are using the ion exchange method, so normally in lab when you are using, we use batch methods. So it can also be used as column methods. And in plants or in big establishments, like it can be used as column methods in industry. But for normal experiment, you can go for batch method. What is a batch method? This method involves single step equilibrium. The resin and the solution are mixed in a vessel like this, pictorially depicted here. You can see you add the resin bead in your solution, stir it, so an equilibrium will be attained until the equilibrium is attained, and then you separate the supernatant. So this method is quite fast and easy to operate. This is used for softening water. So this is known as the batch mode of operation. And this is the column method of operation. The apparatus used in the column method consists of glass columns fitted with a glass wool. So now you can use a column like this where your resin beads are there, and since this is a stopcock, resin beads should not flow through this. Therefore, you have to put some glass wool here so that resin will not come out through this. So the apparatus used in the column method consists of a glass column fitted with glass wool plug or a sintered glass disc at the lower end. And ordinary burette also can be used for this, because you maybe just look at it, it is looking like a burette. So a burette also can be used as your ion exchange column. So that the resin is loaded in the column. Now the solution is slowly poured into the column, and the ions get absorbed on the resin and the mobile phase pass through. So now what is the thing is that, but before preparing a column, now you have to first swell the resin in a beaker outside your column. So first you have to equilibrate it with normal water solution. And if the resin, whatever you have procured, are in some other form, and you want to use it in H plus form or sodium ion form, then you have to change it. So after that, when it is known as a slurry. When it is be well swelled in water or in the solvent, then it is a slurry. That slurry needs to be poured here inside this with a glass wool or a like here some glass wool will be put, and then you have to put the slurry inside the column, and then you load your solution. You need to be separated, load that, and slowly you pour your eluent and let that eluent droplet comes out from this end. So then your ion of interest will be separated slowly. So this method can be used for separation of similar ions like lithium, sodium, potassium, separation of lanthanides, actinides, because depending on their selectivity, they will be flowing slowly through the column, and then they get separated. So use of ion exchange resin is purification of water. The coolant used in nuclear reactor must be highly pure. The cationic as well as anionic impurities are generally removed by ion exchange processes. So now pre-concentration of valuable metal ion can be carried out using ion exchange methodology. For example, pre-concentration of uranium from seawater, that can some amidoxine functional group will be there in the ion exchange resin, and that amidoxine groups are very selective to uranium. So you can put the sheets of amidoxine in seawater, and then it will pick up the uranium. Then that can be eluted in your outside. So separation of uranium from seawater. Now let us see the chromatographic techniques of separation. So chromatography is a separation technique used to separate, identify, and quantify components in a mixture based on their differential distribution between a stationary phase and a mobile phase. So classification of chromatographic techniques are normally, it is based on different chromatographic techniques are there. So classification are basically three types. First one is based on physical state of mobile phase. Here you can have gas chromatography. So mobile phase is a gas, for example, helium or nitrogen. Then there is a stationary phase, normally liquid or solid on a column. So that liquid also not be just a liquid, it will be liquid will be supported on solids. So that will be the stationary phase. Examples: separation of volatile organic compounds. In many samples, you can do using a gas chromatography. Then there is liquid chromatography. The mobile phase here is liquid, as the name suggests, because all these classifications are based on the mobile phase physical state. So liquid chromatography means definitely the mobile phase is a liquid, for example, water, methanol, acetonitrile, etc. Then there is a stationary phase, either solid or liquid on a supporting material. Example is SPLC for drug analysis. Now there is supercritical fluid chromatography, or normally SFC. Mobile phase, again, as the name suggests, is supercritical fluid, and mostly carbon dioxide is used for this. Example is separation of complex mixtures in food analysis. Now, based on another criteria is that type of stationary phase. Also, you can separate your chromatography, like classification of chromatographic techniques are there. So that is adsorption chromatography. The separation is based on adsorption of analyte on a solid stationary phase. Example is column chromatography using silica gel. Partition chromatography, separation based on partitioning between two immiscible phases. For example, paper chromatograph. Ion exchange chromatography, separation based on ion exchange interaction between the analyte and charge groups on the stationary phase. For example, water softening using ion exchange resins, size exclusion or gel filtration. This separation, as the name suggests, is based on the molecular size, with larger molecules eluting first. For protein purification in biochemistry. Then affinity chromatography. This separation is based on specific binding interactions between the analyte and the ligand on the stationary phase. So antibody purification. These are the various classifications based on a stationary phase. So now the third type of classification is based on chromatographic techniques is the planar chromatography. That means the separation occurs on a flat surface. So now paper chromatography, you know paper is a flat surface, so it is a planar chromatography, or thin layer chromatography, that you are making in a glass plate, the silica gel is coated. So that is thin layer chromatography. So these are examples of planar chromatography. So this is used for separation of pigments. You can do it at home also. Actually, if you are taking some sketch pen and putting that ink on a filter paper and then dipping it in alcohol at your home, you can separate the various colors of your sketch pen like that. That is the paper chromatography. A thin layer chromatography, checking purity of compounds, it is used. In biology, mostly these things are used. Column chromatography, so separation occurs within a column fitted with the stationary phase. So under this, again, you can put the HPLC, fast protein liquid chromatography, and gas chromatography. They can again come together in the column chromatography. Now, what are the various applications of chromatographic techniques? In all the field, wherever you just think of widely, everywhere you found the use of chromatographic techniques. See, it is pharmaceuticals, food industry, environmental, clinical, biochemistry, everywhere you can find the use of chromatographic techniques. So these are very versatile, widely used across scientific field for the separation, identification, and quantification also of complex mixtures. The selection of a technique depends on the properties of the analyte, the sample matrix, and the required separation efficiency. How a typical chromatography process goes. This is the pictorial depiction, how a typical chromatography goes. Like this is your column, say, if in a column chromatography, this is your column. So now you have injected your sample here at T equal to T0. Now the sample is present here. So, and then your mobile phase started flowing. So now you can see slowly, depending on their affinity or their interaction of the analyte with the column, now slowly your analytes are being separated. So at T equal to 5 minutes, there is slight separation. whereas at t equal to 10 minutes, if you can see, then there are more separation. So this separation is because the interaction of the components varies with your stationary phase. So chromatography can be used for separation, identification, as well as quantification purposes. So this is what. Now let us see gas chromatography and HPLC. We'll be looking in class ahead. Just I want to tell something about supercritical fluid chromatography. Which is this? This is the refers to supercritical fluid, refers to a substance that exists at a temperature and pressure above its critical point, where distinct liquid and gas phase do not exist. In this state, the fluid, it is not, I am not telling it as a liquid, it is a fluid which exhibits properties that are intermediate between those of a gas and a liquid. The critical point, what is the critical point? It is the point where the temperature and pressure at which the distinction between liquid and gas can no longer be made, and the liquid and the gas phase of a matter coexist. So that is the critical point. Density of supercritical fluids are normally 200 to 400 times higher than respective gaseous states, and that is why they impart increased dissolving power of any solute, just like liquid. Now, the gaseous nature imparts high mobility, and it helps in easy pass through the porous media or separating column. Because of this, supercritical fluid has been introduced as mobile phase in chromatography. Now, carbon dioxide is the widely used or best fluid in case of supercritical fluid chromatography because of its compatibility with the FID detector and low critical temperature and plenty of availability, of course. So this is what. Now, typical applications for supercritical fluid chromatography is that is extraction of large biomolecules, drugs, herbicides, natural products, food products, caffeine from coffee seeds without damaging the coffee seeds. You can extract all the caffeine from the coffee seeds without damaging the coffee seeds. So that coffee seed will remain intact and the caffeine will be extracted from that. Nicotine from tobacco, elaichi flavor from elaichi seeds, etc. are the widely used applications. In biomedical science, supercritical fluid can be used to analyze a wide variety of drug compounds such as antibiotics, prostaglandins, steroids, vitamins, barbiturates, anti-inflammatory agents, etc. And even in nuclear industry, removal of uranium from contaminated tissue paper used in radiological laboratory are done by this technique. So now just I wanted to give one picture for how that supercritical fluid chromatography is used in industry is that you can just see these are the food processing byproducts. These are the food processing byproducts. Some fish thing is there which normally has to be thrown out to the environment, but that will be they will be hazardous to environment, and it is also not like economical. Then health hazard is there. So now they will sort it, and then useful products from these will be extracted by supercritical fluid chromatography. Lipoproteins, capsules for blood pressure, heart function, etc. All these useful things can be extracted from this by supercritical fluid chromatography, and then you can see this is the unit how it looks like. So recovery of healthy valuable components from marine and agricultural food processing byproducts are done by this type of technique. Okay. So this is what all about in this lecture. Any question from anybody? You can ask. So anybody wants to anything? So, okay, now we close this and you can actually mail me or anything because anyway, finally you are going to have one exam. So be ready for that and prepare well for that. Okay.